This is a lesson video to go over some of the answers to 9-5 Day 2. So if you don't need parts of this, you could skip ahead. Remember, you were assigned the evens, and part of what we're really working on is not just knowing the circumference and formulas like that. It's knowing how to give calculations the way that upper level math will need them going forward and how to take those directions and make sense of them. So the first three were really straightforward. They told you no approximations. They said in terms of pi. That means if pi is supposed to be in your answer, it stays the pi symbol. If pi is not supposed to be in your answer, then nothing happens. If your answer is just supposed to be 7, it would just be 7, but no approximations. So they were very explicit in telling you that. So in number 2, they gave you radius, they want circumference. It's a matter of knowing that radius and circumference are both in which of the formulas, and you can see what I did. So circumference will be 2 times pi times 5 centimeters. Putting the labels in will make sure that when I multiply on this side and write it as I can in its simplest form, that my units are in there. Same with number 4, they gave me a diameter. So again, I'm going to use the formula that relates diameter and pi. I'm not going to approximate, and I'm going to use my unit labels. So my final circumference, the 5.5 usually gets moved to the front. Pi gets tacked on as if it were a variable, but we know it's a constant. And in number 6, they gave me the circumference and want the diameter, so the formula I chose to work with relates those two. So then my 46 pi meters will be pi times diameter. In order to solve for diameter algebraically, I would need to divide both sides by pi. And as you can see, the algebra is the easy part here, steering us from a formula that we created to our final answers. Then when you get to 8 through 12, you had to create your equation by reading more information and making more sense of it, and they changed the directions. So in number 8, they want our answer to the nearest foot. That means at the very end, I round one time and one time only. So a picture would be a good idea. They're telling me about a Ferris wheel with a radius of 90 feet. So I'm imagining a circle like that. And they would like to know the distance if I were sitting in the seat that I'd travel in one circumference. So we've talked about one revolution being one circumference. So I need to calculate a circumference for this Ferris wheel and then round to the nearest foot. Because I have radius, my circumference formula that I'm going to work with is 2 pi r. So 2 eventually multiplied by an approximation for pi multiplied by 90 feet. If we had to give an exact answer, that's 180 pi feet. But they asked us to round, so with that much information as our work shown, we can switch to an approximate. And they said to the nearest, so now is the only time I round. And I'll be 565 feet. Number 10, when they describe it, a picture would be a very good idea. They describe a circle of a certain circumference, and it's circumscribed about a square. So it goes around the outside of the square being tangent to it in 4 places, making that nice cyclic quadrilateral. And they've given me the circumference. So as I look at my picture, they're asking me the length of the diagonal of the square, and the diagonal of the square happens to actually be the diameter of the circle in my picture, so I'm really looking for diameter, and I was given circumference. So again, I'm going to relate circumference and diameter, put in information that I know. I forgot my units. Divide both sides by pi, and my diameter was 16 inches. In number 12, Orville and Wilbur. This is another one. Again, we're going to have to decode what they've told us and then see what they're looking for. So as I'm reading it, they're telling me different things about the plane that they're flying, and they're flying it on a path with a radius of 28 meters, so I labeled that. He clocks the plane at 16 seconds for 1 revolution. And I'm going to keep that in mind because that's a nice ratio. It's relating to amounts that I need to work with. However, they asked me the speed of the plane and told me to express it in meters per second. So my goal is to get a meters per second number. It looks like they rounded to the nearest whole to give a true meters per second. It should be more explicit than that, but we'll take it to the whole meters per second. So here's the fact I have to work from, and I want to get it to a certain number of meters per second, so I'm going to back up. The fact I have to work from is that it took 16 seconds for 1 revolution. Well, that also means it took one revolution 16 seconds. So when I write my ratio, I'm going to put seconds in the denominator because of my answer. That's where time needs to go. And then I'm going to put one revolution in my numerator because that's where distance needs to go in my final answer. I need to get that into meters. So my goal is to change one revolution in 16 seconds into some meters per second. Seconds is already the label in my denominator, so I need to change that one revolution, if I can, into meters. One revolution we know is one circumference. So I have radius, so 2 pi times radius will get me into meters. And with my denominator of seconds ready to go. And so while it didn't say really explicitly to go to the whole, we will round to the nearest whole meters per second when we get this. So it'll be 56 pi in the numerator. We're going to be dividing by 16, and that comes up almost to the number. Even if we rounded to the hundredths, we'd still be at around 11 meters per second. 14. Then they start talking about one of my favorites, is the Flintstone National Forest. And if you ever saw the Flintstones, the old cartoon, Old Fred. So as they describe what's going on and they show you the tree ring, what we really want to think about is that if its circumference is 766 centimeters, they tell us that it grows half a centimeter, the ring does, every year. So they want to know how old it is. And as I look at this, they're telling me that every ring is a year. So one ring, 1 year, two rings, 2 years. So as I look at this, in 2 years from my center, I would have had to go out 1/2 a centimeter, 2/2 centimeters from my center to be 2 years old. So I really need to know how many half centimeters are in my radius or how many whole centimeters are in my diameter. And I could choose to do that either way, so I'm going to use the half centimeter amount. So I need to find out how many half centimeters are in my radius, so I need to find the radius of Old Fred. So they've told me that the circumference of Old Fred is 766 centimeters. And if I switch this over to being something that lets me see radiuses, I'll have that. And then to get radiuses alone, I'd have 766 centimeters divided by 2 pi. Please be careful when you calculate this. Both the 2 and the pi are dividers. So if you get an answer of 1,203 point something, you've miscalculated that. You need to go back and make sure you either put parentheses around the 2 pi or make sure that each of those values ends up being a divider. So I'm going to keep the number on my calculator screen active because I don't want to round this off, but I need at least an idea of what to write down. So all these values. So that's the radius of Old Fred at the moment. And every half centimeter of radius represents 1 year. So I want to divide this and see how many half centimeters are in here. And this was, by the way, a centimeters, and it'll be over a centimeter, so the centimeters will divide out. And so as I divide by 0.5, I get about 243.8. And so as I do that, Old Fred must be in his 244th year of life to have that happen. And finally, the last one, explain why. And the key does not give what we would say for an honors math class is a full explanation of why. It does talk through a few good things, so let's take advantage of what it says, but then let's add and make a better explanation than even what the key had, because they didn't really give us our reasons. So we do know that with that 141 degrees, that there'd be a 39-degree angle right there, because those would be a linear pair of angles, and this should be in your explanation, because what you're working on here is proof. So this is by linear pair conjecture. And if that's true, isosceles triangle conjecture says if it's isosceles, then our base angles are congruent, so I'd be moving that over. And then I see two angles that help me decide if I have parallel lines. I see those two. They are corresponding angles, but they don't really finish this off and tell you why. They don't tell you what says if your corresponding angles are congruent, then your lines are parallel. And so line M is parallel to line N by converse of the parallel lines conjecture. So you should be giving us more than the big idea that the answer key gives as your rationale, and you're working on proof and reasoning there.